And welcome back to 13.2 notes. Right now we want to actually talk about how we can measure the pressure inside of a container. We've been talking about how if as you change the temperature, the vapor pressure of a liquid is going to be changing along with it. But how do we actually measure this pressure? Well, one device that we can use to measure pressure. Let me get my pen going here. Get the right color again. There we go. One device that we can use to measure the internal pressure of a gas is a manometer. Okay, and here's a manometer right here. I'm going to draw one off to the side real quick because I want to show how this thing works, and then we'll talk about what this diagram is. So here's our flask, and it's got a little stopper on it, and there's going to be a glass tube coming out of that, and it's going to come to a J shape or a U shape. And that U shape is open to the atmosphere. So there's the U shape. So here's your air out here, and here's your gas in here, and a little bit of a liquid in the bottom. Yep. But what happens is if you put some mercury in here into this tube, this is Hg, which is mercury. What's going to happen is the air is going to be pushing down on the mercury, and the gas is going to be pushing out and down on this side of the mercury. And so what will happen, let me change the color, maybe you can see that a little better. Once again, the air is pushing down, the gas is pushing out. And so you have a pushing match between the gas that's inside the container on this side and the air, which is on this side. Well, if the two pressures are equal, then the mercury levels will be at equal levels. And so if you know the pressure of the air, let's just say that it's 760 millimeters of mercury, then you'll know that the gas inside of this container is also 760 millimeters of mercury, because they're at equal heights and they're equally pushing on the mercury. But what could also happen is that the gas might actually push out more on the mercury than the air is, and that's the case in this first container. These gas particles, this happens to be ethanol, is pushing down on the mercury, and it's actually forcing the mercury back up into the tube a little bit. So you know that the pressure on this in this ethanol is stronger than the air that's pushing down outside of the manometer. And as it turns out, you can see here, it's 12.2 millimeter difference. So if the air is still 760 millimeters of mercury, which we measured with a barometer, and the ethanol vapors is 12.2 millimeters of mercury stronger than the air, then that would mean that this ethanol must be the 760 plus the 12.2 that it is stronger, so it would be 772.2 millimeters of mercury. Now, if you heat this thing up, as you would expect, more particles are going to go into the gaseous phase. More particles in the gaseous phase mean that they're going to be pushing harder down on the mercury. The air, which we're still assuming is going to be 760 millimeters of mercury on the outside, is actually being the mercury is being forced up and out even more. And according to this diagram, 43.9 millimeters of mercury stronger than the air is pushing down. So therefore, in this case, this ethanol vapor has a vapor pressure of 760 plus the 43.9 millimeters of mercury, which is 803.9 millimeters of mercury. So that's how we figure out what the pressure is on the inside of these things, is by using a manometer. Now today we just use a digital manometer, and it works a whole lot easier, but that's the general idea behind these things. Okay, so moving on, scrolling down. Let's talk about boiling point just for a second, because that's one of the properties of a liquid that's affected by the attractive forces of the particles. The boiling point, and we're going to switch back over to our green. The boiling point is the temperature at which the vapor pressure of the liquid is equal to the external pressure. Now, why is that? Well, because if you have a container, here's your liquid, here's your particles, you have pressure pushing down and keeping the particles in the liquid phase. Some of these particles want to escape into the vapor phase. The temperature at which these two pressures are equal is that middle ground, or that equilibrium point where the particles can in fact escape and go into the vapor phase. And that's the point at which a liquid is going to boil. Now, what temperature is that? Well, it depends on the external pressure, because at sea level, let's go ahead and scroll down here. If you start increasing the temperature, pause just for a second here. All right, so again, we're at sea level here. At sea level, on average, the external pressure is going to be 101.3 kilopascals, or 1 atmosphere of pressure. If you start heating the liquid up, here's our burner right here. As you start heating this thing up, say we're up to 70 degrees Celsius, the vapor pressure of the water is not quite 101.3 kilopascals, so the water doesn't start to boil. Once you get the temperature up to 100 degrees Celsius, as we are here in the second picture, now notice the water is starting to bubble and starting to boil. Why? Because the pressure of the vapor pressure of the liquid is matching that of the atmosphere, and so the water can now escape into the atmosphere. It can push its way out as the air is pushing down. Think of it as a pushing match. The air is pushing down and trying to keep the particles in the liquid phase. But once the vapor pressure of this liquid matches that of the air, now they can push their way out. It's a stalemate, which means they're at equilibrium, but what actually happens is you start giving it more and more energy as it boils, and in fact can force its way out. So that's what happens when a liquid boils. It's just that the vapor pressure matches the external pressure and it can push its way out. Now, if you go up on top of Mount Everest has less pressure pushing down. There's just a little bit of pressure pushing down on the liquid, keeping the particles in the liquid phase. So it doesn't take much energy. In fact, in this diagram here, it says at 70 degrees Celsius, now they have enough energy to escape into the vapor phase. And so water boils at lower temperatures the higher the elevation is. I think in Denver, Colorado, water boils at, say, 85 degrees Celsius. Now, you might be scratching your head and saying, well, wait a minute here. I thought water boils at 100 degrees Celsius, and that's what the boiling temperature is. That's actually what is known as the normal boiling point. The normal boiling point is the point at which the vapor pressure matches 1 atmosphere. So I'll just say vapor pressure equals 1 atmosphere. And it takes water, you have to get it to 100 degrees Celsius before it's actually going to do that. But water can boil at any temperature depending on the external pressure. It's just we're typically talking about 1 atmosphere. Okay, scrolling down. Last thing we want to talk about here. Looking at the vapor pressures of various liquids. Here is 1 atmosphere of pressure, which is 101 kilopascals. At what temperature does the vapor pressure of a particular liquid get to atmospheric pressure? Well, at water, here's water along the red line here, so I'm just tracing it in green. It takes 100 degrees of temperature to get the vapor pressure of water to match that of 1 atmosphere. Ethanol and chloroform actually boil at lower temperatures because the particles are held less tightly, so it takes less energy to get them to that vapor pressure. Ethanoic acid has stronger intermolecular forces, so it takes more energy to get them into the vapor phase and to the vapor pressure that matches atmospheric pressure. Okay? If you need more details on that, we'll talk about it in class.